Okay, so good morning, everyone. Uh, so we are going to continue. I hope we can finish. Last time we discussed the separable equations, and I would like to move to another method. But I would like just to review a little bit and maybe giving you another example. And I think next week, 28th, Thursday, I think we are going to have a quiz. September 28th. So that will be, I think, all the contents from the beginning. And then if you remember, we have the direction fields, right? And we have I call that the phase portrait, the autonomous differential equations, separable equation, and also later we are going to see the linear equations that will be, I think, also included within the quiz. So 1 hour, okay, on 1 hour class. Okay, now let me start by reviewing the separable equations. Okay, so let's solve. Okay. Hmm? Y prime. Remember that the y prime is the y. It's a little bit tricky. But since we only have a separable equation, that's the only way we can solve. think the first step, I think some students get it correct. So the first step is to factorize. You can factor this out, right? So you can factor this, I believe, 1 minus x squared, right? And 1 plus y squared, okay? And then if we get this, then we can simply separate x and y. Okay? So we could take this. Let me write dy dx. Okay, and then we can move all the components. So y components I will put on the left. And x component on the right side. Okay. I think we can simplify it. This one's still 1 over 1 plus y squared. And this one becomes 1 over x squared minus 1, right? Okay. And I think we can just integrate. Okay. So if you have, I believe you can integrate the left equation and the right equations, right? You can integrate the left one becomes what? 1 over 1. Yeah, tangent inverse, right? Or arctangent. So take that into integration. So this will be tangent inverse y. And then 1 over x squared becomes negative 1 over x minus x. And then let me just add a constant on the right side. And you can write the equations y, our solutions, is equal to tangent of all this negative 1 over x, negative x plus c. But since we have the initial conditions, we could check when x equal 1, y is 0. So we check when x equal 1. So 0 equal tangent negative 1 plus c. So we get that c should be 2. So our solutions become okay. Another notes that I would like to share with you is maybe let me give you another example. Let me get you to let's say we have dy dx equal let's say you have this, it seems simple, but when you realize that the exponent with the power of negative x squared is not a regular function, right? But somehow we need to propose our solution. So if you look the functions or the equations, this expression E, this is what we call, if you remember the terms, is what we call the non-elementary. Which means that it is not integrable. Okay. But still, we need to propose some solutions, right? So one way to write down the solutions is, first is we are using, we call the, let me write dummy variable. Usually dummy variable is dt, if you remember the relations between derivative and integral using fundamental calculus. So we could take that, let me write this dy dx. So we could take dt to both sides and then integrate with respect to dt from x, or from 2 to x, sorry, from 2 to x. 2 is from this one, okay, from the initial condition. This is also the same, and change this x with t. Okay, by doing so, we are getting that this is from 2 to x, and then we just write for the right equation just as it is. We call this the integral defined equations. And then we can write yx minus y of 2 and then we can write yx is y2, or y2 is 6, so we can write 6 plus integral defined function like that. Okay. So this is what we call integral defined function. So the general terms is, let's say yx, and then y0, the initial condition, plus g of t dt. And then we need to define that g of t, or integral g of t dt, is non-elementary. Okay. Okay, now we can move to the next section, which is what we call the linear equations. Okay. So let me write the form first. So let me write a1x dy dx plus so this form, we call this is linear equation. In the dependent variable y. Okay. We call in terms of g of x, if this equal to 0, then we say the linear equation is homogeneous. If not 0, then linear equation is non-homogeneous. Okay. And this form we can rewrite, and taking the constant, we take out the constant and we get dy dx plus, let the coefficient become p of x, y, and then equal f of x. So we call this the standard form. And now the solution, the proposed solution, it has at least two main solutions. So the total solution we call y equal, we are going to have yc plus yp. Yc is solution for a homogeneous equation, and yp is particular solution for non-homogeneous. Should be later. Okay, suppose this is our solutions to the differential equation. So suppose, number right here. So suppose y equal yc plus yp is solution for differential equations equal or dy dx plus p of x y equal f of x. Okay, which means that if we plug in the solution, then it will satisfy. Okay. So let's try to make it into our solutions. This one, I think, let me cut first and make it to here. Go back. Okay. So I will take y inside these differentials. So yc plus yp and then plus p of x and then y. And basically, we are going to have each the same expression with each of these yc and yp. So we have d dx yc plus p of x yc and then plus d dx yp plus p of x yp. Okay. And this should be equal to f of x. Okay, now the homogeneous is equal to 0, right? So we can take this equal to 0 for non-homogeneous, for homogeneous, sorry, for homogeneous. So let's try to look at this homogeneous first. So for homogeneous, okay, for homogeneous, we can try our separable equations. So we can take the we can divide by y and multiply with dx. So we get dy over y plus px dx equal to 0. Okay. And if we solve this, we are getting yc is constant e with the power of negative of px dx. Okay, this e is become it's coming from the ln, right? 1 over y. So you could take this if you want. You could take the separable equations, and let me write here, and then take integral. This will be ln y, and this will be let me just write as it is, and then y is e But for simplification, let's write the yc here as c y1 x. So let's simplify the e, the exponent first. Okay, this is just to simplify for our process. And y1 is this. Okay, so this is for homogeneous first, and it's still not yet a complete method. Okay. Okay, now I will move to the non-homogeneous, okay, and then we are going to combine at the end. So the non-homogeneous, we are going to use one procedure called the variation of parameters. So the idea, let me write, the idea is find a function u so that our yp equal ux y1x, or it's equal to ux e with the power of negative px dx is a solution of dy dx plus p of xy equal f of x. So we are going to use the yp equal, let me write in a simple way, u y1, okay. And we are going to substitute yp into this differential equation. So substitutions. So ddx of uy1, okay, and then plus p of x, and then we decide to have uy1. Okay. So we are going to force this to make it fit within our differential expressions. Now, since u and y is also variable functions, then we are going to take the derivatives with the product rule. Okay, so take the product rule. So this becomes u dy1 dx plus y1 du dx. Okay, and then plus p of x u y1 equal f of x. Okay, and then we can groups this u with this u. So let's take that. So u dy1 dx plus p of x y1 plus y1 du dx is equal f of x. Okay, so since this is y1 is the same as what we mentioned here, and oh, I forgot to mention that this is, so in terms of this y1, so if we take the y1 dx plus p of x y1, this should be getting to be 0. Okay, because it will be minus and then plus, so minus e plus e is 0, right? So it will be 0. So this will conclude by 0. Then we are going to solve, let me write here. So y1 dy dx equal f of x. Oh, not dy, sorry, it's du, right? And then du will be f of x divided by y1, because y is a function of x. Let me write y1 as y1 of x. Okay. And then take integrations. So we are going to use the separable equations. So we get that u is integrations of f of x over y1 of x dx. Remember that y1 is e with power of negative of integration px dx. So we can say that 1 over y1 is just e with the integrations of px dx on the power. Okay, let's get back to yp. We assume yp is uy1. So we can exchange u can exchange u becomes integrations f of x over y1 of x dx. And let's say this is also y1. And we exchange y1 and 1 over y1 with the terms e that we have on the right side. Okay. So yp equal. So y1 is e to the power of negative integrations px dx. And then fx over y1x, this will be integrations of e with power of integrations px dx, f of x, and then dx. Okay, so we have yc, we have yp. Now we combine both of them. So combine yc and yp. So y equal yc plus yp. Okay, so y is yc is c e negative px dx. And then plus we combine all of this e with power negative px dx. And then integral e power integral. It's really complicated, it seems, right? And do we need to do all of this? You will see later that we can have a, I think, better understanding how to look at this. Well, let's simplify it. Let's multiply this with e with power of integration of px dx to remove the e with power of negative, right? So we can remove this and this, right? So we have y, or we already multiplied, right? So multiplied e y, and then this is constant plus e f of x dx. Okay. Okay, let me copy this and later continue. If you want to write notes, you can write first. YC, YP, I think in the first order, and later when we learn the second and then the higher order, you will see a lot of solution will include this YC and YP. And these two type of solutions will be very, very important in the next method. It's not done yet. In principle or in practice, the linear equation will be, I think, one of the applicable method that you can use for most linear equations. So for most first order linear equation, you can focus on the linear equation method. So the idea is now we have this, right? So we have something with power of function of x, and we have also y. Now the idea is we are going to find what kind of functions that when we set up some product rule, it will have some results that is similar. So let me go through the new page and then copy the one that we did. So this is the result. Okay. So if we take derivative, and then let's say we are going to derive this. And then take derivative, constant becomes 0, and the integral will be removed, right? So we are going just to have e okay, and then we set up a product rule for this one. So this will be e dy dx, and then plus p of x e and then y, and then this equal to e so it seems that we have something for all the expression within this equation. We have this, right? We have this e. And if we remove this e, just divide by this expression, we get directly the same expression as we did from our original expression, right? We get back to the original one. So finding this e is important to let the process coming to a solution. So we can take this e. So this e is actually, we can say, this is what we call the integrating factor. Sometimes we write as mu or r, that is equal to e with power of integrations px dx. So what's the deal? So if we can find an integrating factor, and then we multiply to the linear equations, and then we can set up this as a product rule, then we can move from this product rule result and go to this. Okay, do you get it? So it's actually pretty simple. What you need to do is find this. Find the integrating factor, multiply to all expression in the linear equations, and you need to force out this becoming a product result. And then go here. So I think it's better to use some example so that you can have a so solve. Okay, we can take a break first. The linear equations, if you read this guideline, so basically we are going to make a standard form, and then we are going to pick and determine the p of x. And then after that, we take the p of x and compute the integrating factor. After that, we multiply all with integrating factor, and then try to just be doing the integrating both sides. Okay. So what does it mean? It means that with the first one here, let's write into our standard forms. So let's write. So the standard form, let me write, go down. So this becomes dy dx plus 4y equal e to the power negative x. Remember, the standard form okay, so this will be f of x, and this 4 is p of x, right? And then we can take the integrating factor is equal to e. Let me write the formula first. This will be e for dx, or this is just e with power of 4x. Okay, do not add a constant here. So this is simplifications. And now using this e, multiply all components. Let me just write again. And then multiply e. Okay, we multiply. And now we need to think, if this is the product result, what will be the previous part before we derive? So what does it mean is we are going to make this in this form. So we are going to fill this blank with some equation that when we derive, it will produce this. Okay. Now of course you see we have e to the power of 4x. And remember exponent, we derive it becomes the same, right? The same exponent with multiplication of the chain rule. Okay. So I think we can take this and let's say, and sometimes we just take sometimes to try and error. Okay. But it will be very, I think very quick. So we can take, perhaps this is going to be e for x and y. So we can check. So e for x, y. So dy dx, e for x, okay. And the other part, e for x, we multiply 4, y. I think this is correct, right? If we derive this, it will have this result. Okay. The right side is just, we take this and, okay, we have e to the power of 3x. And then we remove this e dx with integral. So take integral. And then we get our implicit solutions. And plus constant. We can somehow divide. Let's say this is maybe C1. So we take y and then e. And then this will be 1 over 3 e negative x plus and then since we also have the initial condition, which is this, right? So let me write that y when x0 is pi over 3. So when x0, we'll have 4 over 3 equal 1 over 3, and then plus the c, right? And then we get that c is just 1. So the solution, we can write, the solutions then is y 1 over 3 plus e with power of negative 4x. And then this will be our solution. Okay, let's have some practice. Okay, to getting used to this method. So the idea is multiply the integrating factor, okay, and then finding this TDS of the product, which when you derive, it will be giving you this linear equation multiplied with the integrating factor, and then take integrations, and then that will be your solution, and then you can solve. Depends if the questions give you the details of the condition, then you can set up the initial value, and you get the exact solution. Or maybe still you still have the constant like this, still okay. But remember, you can do this part if you are sure that it is on the linear equation form. If it's not, then you need to use another method. And of course, within the process, sometimes you will see some derivative or integral that needs some techniques from calculus 1 or 2. So you need to do some review by yourself. I can give you some clue, but I don't think I can cover all the techniques. So I hope you still remember. Okay, let's get to another example. Okay. Solve and no initial value, so you will still have a constant in your solution. Let's try for a couple of minutes. Let's try first. Okay, so first we are going to make a standard form. So we define all equation by x to make this. right? And then we identify, okay, this is f of x, this is p of x, right? And then we take this p and use the integrating factor to negative 4 1 over x dx, right? And then we get that this will be negative 4 ln(x), okay? So we are sure that this is ln(x), not ln absolute value, because we know that the p and f are continuous on the positive value, right? So we can take the integrating factor and solve this, and this e will become e ln(x) negative 4, right? So we can cancel this, and then we have the the mu, or the integrating factor, is x with power of negative 4, right? And then multiply to our standard forms. So we get dy dx, and then x with power of negative 4 minus, so we multiply and it's become the 4y, or maybe let me just write 4, and then x with power of negative 4, negative 1 is become negative 5, right? And then this will be, or let me just write negative 4 first. Negative 4 over x, and then x with power of 5. Okay. And then we can solve this. And then we need to find the product rule. Oh. Okay. So the product rule, which resulting in this x with power negative 4 dy dx minus 4x with power negative 5y. It seems that perhaps this x with power negative 4 will be, I think, will be our clue. So I think this will be x with power negative 4, and I think y, right? Because negative 4 with the right, it becomes this one, right? And then this one, okay? Okay, now we integrate both sides. Integrate both sides. So this will be x with power negative 4y equal, what is the integration of this? Remember, this is integration by parts. So let me write here just to make some notes. This is 1, 0. So this will be x e to the x minus e power of x plus constant. Let's say constant 1. And then y is x
5. And that will be our solution.
Okay, any questions about the linear equations? Okay, I hope you get the procedures correct. So remember the standard form, taking the integrating factor by taking the px inside the e, and then multiply the standard form with the integrating factor, and then take the product results, and then make it into the product form, take integrations, and that will be our solution. Okay. I think the difficult part is not the equations itself. It's not the method itself. I think some of the part that makes it quite complex is sometimes you have some algebraic expression that you need to be simplifying, or some techniques in calculus 1 or calculus 2 which you are forgetting. That's the problem.
Okay, one note. Let me give you another example. Okay. So find, or let's say solve. So solve Okay, try this one. Okay, now if we want to make it into linear forms, as usual, we take this. Okay. And now we know that p of x is this, and f of x is equal to 0, which means we are going to have a homogeneous. Remember that when we identify this p of x, as x over x squared minus 9. Remember the continuity of the functions. Okay, so if we take this, which means that p is continuous, so we have something on this x equal negative 3 and x equal 3, which makes the function maybe not continuous over there, right? But let's say we are going to try to make our solution first. Okay, so we take the integrating factor, we take e integrating x. Okay, if you forget, I think we can take the substitutions. So let u so half 1 over u du. This will be half ln, and we're not sure it's negative or positive, so ln will be x squared minus 9, like that. So our integrating factor will gives e half ln x squared minus 9, or we could simply write this, and since it's roots, then we can make sure that we can just write this square root of x squared minus 9, and then multiply the formula, we get dy dx and then we know that this will be, or before that, let me simplify this. Which one? Oh yeah, what? So let me write so plus xy, this will be or maybe let me write it's going down. Okay, then it's equal to 0. And then this will be d dx. This is square root of x squared minus 9y, right? And then if we take the integrations both sides, this will gives you equal a constant, right? And your solutions, it seems constant divided by square root of x squared minus 9. So either on this interval, solution are this. And this 3 and negative 3, we call that, if you remember, x equal 3 and x equal negative 3, they both are a singular solution. Right? So you need to be aware of the singular solution. Usually it will comes up when you are having some discontinuity on your functions. So perhaps you have a singular solution. Okay. And for the previous example, this one, when we have x equal to 0, this is also singular solution for this one. Okay. Okay, so you need to be careful on the interval. Okay. Okay, now let me give you to the next one. This will be the last one for today. So solve okay, very easy, I suppose. Okay, so if we identify the p of x is just 1, right? And this is f of x. So if we want to write the integrating factor, then this will just e to the x, right? So then let me copy. So e to the x, and then e to the x, and then e to the x. And then we see that, I think it's obvious that this is just e to the x and y, right? And take integral. So we have e to the x y. And then this will be let me do the integration by parts again, just to make sure. Oh yeah, correct. So x and then plus constant. So y is x minus 1 plus constant e to the negative x. And then we know that the initial value is when x equals 0, y equals 4. So we can take that. So c is 5. So the total solutions, x minus 1 plus 5e to negative x. Okay, now what I want to show you within this solution here, remember that at the beginning of the linear equations, I told you that the solutions will have at least two main solutions, which we describe as YC and YP. Right? YC is homogeneous, which means the f of x is equal to 0, and YP is for non-homogeneous. Okay. Now, this example here showing you that this part is homogeneous, or we say YC, and this is YP. You can check when the right side is 0, then you're getting the same e with power of negative x without this x minus 1. Okay, so we get it that why? It's not fit. Okay, so we're getting that the 5 multiplied with e with power of negative x, that will be our YC. So we can write YP is x minus 1, YC is 5e negative x. Okay. But I think it will be very obvious. Wow. It's not really good connection. Okay. So every time you have a solutions, I think it's better to split the solutions. Sometimes we may need to configure one part or the other part. So I think the most obvious one is this YC, because we can just make this one equal to 0 and we get the same structure, right, with this. So in this whole solution, we can say, okay, this part is the YC, this one is YP. Okay. And this YC, sometimes we also call this our transient term. What is that? So transient means if we take the limit, or not the limit, maybe as the x getting bigger, YC will getting closer to 0. Okay. So sometimes we are getting this transient term. So what does it mean for this transient? So the YC seems not really too significant, because when we increase x, YC becomes 0. So it means that we kind of somehow, if we take the x larger and larger, somehow we can ignore this. That's the transient term. Transient means we can make the terms negligible or not really significant. Okay. I forgot to put the graphs here, but if you put the graphs, if you take the x larger and larger, and you try to draw the graph will getting close to x minus 1. Okay. Oh, I think we still have some minutes. We'll just add one more. Solve. Okay, we can have this kind of functions. We can have this piecewise function. So the differential equation has this function of x, which we can describe into this piecewise.
how to do it? So we could try both both terms. Okay? We could try when it's equal 1 and then equal 0.
So we have two intervals. So, okay. So the first interval is from the 0 to 1, right? And the other interval is when it is larger than 1, okay, but not including 1. So we could say for the first interval, we can get this equal 1, right? And then by taking the integrating factor, because it's just 1, then integrating factor is just e to the x, then you will get ex dy dx plus y ex equal ex. Then you will get that this is just and take integrations. You will get that. Let me skip some parts and then write the final solutions. 1 plus c1 e with power negative x. And then, because we have the value for initial condition, we can take this c1 is negative 1, right? So we have y1 minus e power negative x. And then the same thing we can do for the other interval. So for interval greater than 1, we take this equals 0. And then we can solve it directly, right? We can just use separable equations. And then we say that this y is equal to, let's say, c2 with power of e with power of negative x. That's our solution. And then the total solution, we can write y. First one is 1 minus e negative x. This is from 0 to 1. And the other one is c2e negative x when x is greater 1. But we need to check the C2. Because it seems if we plug in 0, I don't think we get the solution. So let me write here. So the requirement is we want to make it continuous. So we want to make it continuous. So for continuity, that we take the limit as x is approaching 1 from the right of the function, let's say y, this y function, y of x. This need to be equal with the function itself at x equal 1. Which means that these two need to be equal to make the function continue. Okay. So, or let me write on the right side there. So we need to make this 1 minus e negative 1 equal c2 e -1. So C2 is divided by E -1 is 1, right? E, or is E minus 1, right?
And that means we can change this C2 with E minus 1. Okay. Did you get the idea here? Okay.
So the solution, let me write here, are 1 minus E -x for 0 to 1, and E minus 1, E with power of -x for x is greater than 1.
Okay. Why we cannot directly get the constant here? Because the interval is greater than 1. The initial value that we have is on 0, x equals 0. The interval is only on this one. Okay. So how do we get the constant here? So we need to assume that we are going to have a continuous function, and we want to make the limit is equal to the function itself. So that is the continuous function. Calculus 1, continuity. If you remember calculus 1. Okay. Okay, any question? No? Confusion?
Okay. Okay, as I mentioned before, 28 quiz, okay? 28. Thursday, 1 hour. I think I'm up until the linear equation. Okay. Okay, please scan this QR code.